Hello everyone, my name is Shyam Trivedi. I am postdoc at Institute of Nanoengineering and Microsystems at National Tsinghua University, Taiwan. I will be presenting the work Piezoelectric MEMS vibration sensor module for machining quality prediction in the IEEE Sensors 2020 virtual conference. Beginning with the presentation, this is the outline of my presentation. This work presents the design and fabrication of PZT MEMS accelerometer, followed by its system level implementation, and finally use the module for surface roughness prediction. The fourth industrial revolution, also known by the keyword Industry 4.0, involves automation in manufacturing and production using intelligently connected devices. It mainly composed of four things. First is the sensors, accelerometers, gyroscopes, magnetometers, temperature sensor, etc. All are used for monitoring the conditions of the machine and performing the predictive maintenance. Smart machines and robots for mass production in assembly lines, and the data generated from these sensors is analyzed using machine learning or AI to improve the safety and productivity of the entire system. Finally is the IoT, which is the intelligent network of connected modules or devices that interact with each other to provide the enhanced functionality. Now, accelerometers are devices which sense acceleration. It consists of a hanging proof mass that faces an inertial force in the opposite direction of the applied acceleration. The net deflection of the proof mass is ultimately converted into a voltage depending on the transduction mechanism used. For example, piezoresistive, which involves the change in resistance, capacitive accelerometers, which involves change in the capacitance between the electrodes, and piezoelectric accelerometers that generate charge due to proof mass deflection. Each one of them has certain range and advantages and disadvantages as listed here. Now, surface roughness is an important measure for manufacturing quality. We need a system that can detect the surface roughness without requiring the machine shutdown and mounting and dismounting of the separate instrument. In this case, the low-power piezoelectric sensors are important candidates for the implementation of any predictive machine monitoring system. Accelerometer design. The thin-film piezo on silicon (TPoS) accelerometer was fabricated using GlobalMEMS platform. PZT5A material of 1 micron thickness is sandwiched between gold and the platinum electrodes with 5 micrometer silicon beam thickness. A gimbal-shaped guard ring was designed to reduce the cross-access sensitivity, and a differential output voltage between inner and outer terminals is used to take the differential voltage and reject the common mode noise. The proof mass can vibrate in X, Y, or Z direction. This shows the FEM simulation of mode shape with volumetric strain for each axis of vibration. The guard ring increases the stiffness in the in-plane direction, and for the X and Y direction motion, this leads to a very low voltage generation leading to a low sensitivity. But for the out-of-plane motion, the proof mass, when it vibrates out of plane, it produces tensile stress in the outer electrodes and compressive stress in the inner electrodes, resulting in a large differential voltage, which is about 3 orders larger than the X and Y axis case. The fabrication. The fabrication begins with a 1 micrometer thick PZT coated SOI wafer. We etch the PZT using sodium chloride and HCl, then deposit the cold layer followed by patterning and lift off. The etching of PZT, platinum, and silicon is performed using inductively coupled plasma technique, and finally release the structure using the deep reactive ion etching. This one shows the optical microscope image and the SEM image of the fabricated device. It also shows that the out-of-plane motion will generate voltages of opposite polarities. Module design and measurement. This figure presents a system-level implementation of the MEMS device, the charge amplifier circuit, and microcontroller all integrated on a single printed circuit board. The PZT accelerometer generates charge and produces a corresponding small voltage. This signal is given to a charge amplifier. The analog signal is then fed to a STM32 microcontroller, which performs the A to D conversion and stores the result in direct memory access buffer, and the results are read using the Universal Asynchronous Receive Transmit Protocol via USB. The entire unit is designed as a module, and the results can be seen in our own designed LabVIEW software. A closed-loop shaker measurement is performed for the device characterization and comparison with the reference accelerometer. The design module and the reference device are kept on the platform of the LDS shaker system. The function generator provides a sinusoidal signal to the power amplifier, and the amplified signal is given as input to the shaker system, say for example a 1G load at a given frequency. The output of the reference device is fed to the crystal signal analyzer, and its output can be seen in the proprietary LDS shaker software. The output of our design module is seen in the LabVIEW software via USB connection to the PC. Now this shows the measurement result of the design accelerometer. The top graph shows the time domain plot of the accelerometer at 1G load at 500 Hz frequency. The corresponding frequency domain plot is shown here with a noise floor of -63 dB and a peak shown at 500 Hz. The performance was compared with a reference device, PCB Piezotronics. The device starts to show deviation at about 800 Hz and follows the typical frequency response of the accelerometer. Moving on to the machining quality prediction. The experiment for surface roughness was carried out at the CNC Machine Center using the GT630 machine. The diagram on the right side shows the detailed setup of the quartz disc polishing process. We have a spindle with attached grinding wheel, the quartz disc to be polished, and the AC axis rotatory table. The three main parameters to consider in the polishing process are the spindle speed given in RPM, the feed rate given in millimeters per minute, and the AC axis speed of the rotatory table. This one shows the picture of the actual setup. With the red one is our own MEMS PCT module, and this is the commercial vibration sensor. The first step is to collect the data. After every 30 seconds of polishing, a Keyence lasing scanning microscope was used to measure the surface roughness data at 12 points on the disk, with 4 points each on the center, middle, and the edge, followed by averaging. This generates a total of 54 data sets, out of which 28 are used for training the neural network model and 26 are used for testing. The 28 training datasets are further grouped into 7 classes. This is necessary for performing the essential data pre-processing step requiring the dimensionality reduction using linear discriminant analysis or LDA. This shows the complete flow of surface roughness prediction system. The first step is the data augmentation, involving use of overlapping time sequences. Overlapping helps to increase the diversity of data without actually collecting more data and helps to make the training data more closely distributed and reduce overfitting. Next, we perform the FFT and do the averaging using a window bandwidth of 20 Hz. A very large window, W, can help in noise suppression but will suffer in feature extraction. The band averaging process generates 256 data points. Next, the LDA is performed. The linear discriminant analysis helps to group the data and increase the difference classification between the cluster of data. We calculate the Fisher's linear discriminant index J, which is kind of like an SNR for data classification. Larger J value means the mean of the data are well separated with very less variance within the group itself. The use of correlation analysis is done to reduce the number of data points. Next, the processed FFT data is fused with the feed rate as it has the highest correlation with the surface roughness. The input layer has 46 neurons and 2 hidden layers are used with 28 and 21 neurons respectively. The processed training data is fed to the neural network with feed rate as the fusion input. The data passes through 2 hidden layers and finally generates an output. For any given neuron, the output is obtained by applying an activation function to the weighted sum of its different inputs and biases. The normalized measured surface roughness is compared with the predicted value of the surface roughness, and a mean square error or a loss function is calculated. The backpropagation neural network is used along with the Adam optimizer with a set learning rate to dynamically update the weights. After each cycle, some neurons are dropped out in the hidden layers in order to reduce the overfitting problem. And the process keeps on repeating till the error is minimized. Once the minimum error is reached with the correct weights, the model is set to be trained. After training, the test is performed on the trained neural network to predict the roughness value. This shows the test result. The graph shows the measured and predicted value of roughness for 26 data sets. The performance indices are calculated, and for the LDA technique used in the machine learning process, the mean square error and the mean absolute percentage error of our PCT module are found to be consistent with a commercial sensor. Moving on to the conclusions. This work has presented a piezoelectric accelerometer with guard ring using differential electrical configuration, which helps to reduce the cross-axis sensitivity. The MEMS device, amplifier, and the microcontroller all were designed as a system on a single PCB, and the performance was compared with the reference accelerometer. And finally, we used the backpropagation neural network technique for machine learning. The model was used to predict the polishing quality of quartz substrate by evaluating the indices of performance and compared with the costly reference triaxial accelerometer. Thank you for patient listening and providing me the opportunity to present this work at IEEE Sensors 2020 conference.